Take a brain scan and apply one operation. You get K-space. Apply it again and the image comes back, reflected through the origin. Again, K-space, mirrored. A fourth time, and you are exactly where you started. For applications, and nothing you can see has turned. But nothing was turning because you were watching the wrong plane. Take one line through the scan. Plot it by position and spatial frequency, and you get a second map, phase space. Turn one parameter in both panels. At 90 degrees, the picture reaches K-space. On the right, the line's Wigner map rotates as one object. In this representation, Fourier is exactly a quarter turn. Keep going. At 180 degrees, every point reflects through the origin. Left becomes right, up becomes down. At 360, you recover the original. For quarter turns bring you home. A correctly scaled Gaussian is special. Its magnitude stays unchanged. But MRI does not turn this dial. Each gradient field changes across the body, so the scanner acquires K-space samples instead. Reconstruction transforms them back into an image. So why is that turn exact and not just a picture that happens to look like one? Split the line into special shapes. A Gaussian, then the same Gaussian rippled once, twice, 3 times. These are the Hermite Gaussian modes, and Fourier does something remarkable to them. It does not change their shape at all. It only advances each one's phase at a rate set by its mode number. So define a fractional transform that advances every mode at that same rate through an angle you choose. At 90 degrees, each mode has picked up exactly the phase ordinary Fourier gives it. At 360, every clock has come back. Recombine the modes, and you get the turning line. Its phase space rotates rigidly because underneath, each shape is only spinning in place. And mode 0's clock never turns at all. That is your Gaussian. But what is a turn of 30 degrees as an operation you could actually perform? Write it out, and 3 factors appear. Multiply by a ripple that tightens as you move outward. Take a Fourier transform. Multiply by that tightening ripple again. The ripples are quadratic phase, and the angle sets how fast they tighten. At 90 degrees, they flatten to nothing, and ordinary Fourier is all that is left. Light does this for real. In a graded index fiber, phase space turns as the beam travels. So why does a scanner never use the angles in between? Because a gradient varies the field across the body, writing one stripe of phase, and the coil sums the whole body against it. That is one complex number in K-space. Gradient area picks the point. The coil measures the value. Nothing turns a dial. The scanner measures the endpoint, then transforms once.